Alright, so we're going to start with the parallel circuits. So we know that if you're not speaking, please keep your mic on mute. So parallel circuits are identified on the basis of the idea that current may have multiple choices or multiple paths to go through, right? And we understand that the formula to find out the total resistance is 1 over RT equals to 1 over R1 plus 1 over R2 plus 1 over R3 and so on, however many resistors are added in parallel to that particular setup. So in parallel we have two rules. The first one is that the voltage remains same. And from yesterday's lesson, if you remember, from the last lesson, you may remember that in series circuit the current remained same because there was no alternate path. Here the voltage remains the same, and we will explore the reason for that as well. Keep in mind that voltage, we know that it's the energy per unit charge, or it's the energy or work done per unit charge, or you can say the amount of energy spent or brought into the circuit by each electron or each packet of electron. And this idea will help us understand why voltage remains the same. Okay, so point number two. Current divides. Now, because the current has multiple paths, it's going to divide. If you remember, in our previous lesson, we did find out that the logic for the division of voltage in series circuit was that higher the voltage, higher was the resistance. Do we remember this from the yesterday's lesson? Yes or no?
Yeah.
Over here, the division logic of the current is a bit different, and of course not against the intuition, but we're going to explore how it is. So since we have the formula for Ohm's law is V equals to IR, and we are saying that the voltage is constant from point number 1. So let's bring resistance on the other side, so we are left with V divided by R equals to I. If I rearrange this to make I the subject of the formula, we get I equals to V divided by R. Now since V is constant, I can ignore this for the sake of proportionality, and I can write down that I is proportional to 1 over R. It is inversely proportional to resistance. What does this mean? It means that for whatever branch the resistance is higher, the current through that branch will be lower, and vice versa. So what do we mean by that? For example, if I had two branches of resistors and one of them had a higher resistance, let's say one of the branches has 20 ohms and the other branch has a resistance of 5 ohms, a clear difference between both resistances. The current that enters the junction or enters the node will be the same as the current that is going to leave the junction, because after being separated, they're going to combine together at this node and then carry on to the rest of the circuit as well. Now let's say that this is current I1 and this is current I2. I can very well say, just looking at these values of resistances, that my current I2 will be greater than current I1. 5 ohms will receive a higher share of the current entering the junction as compared to 20 ohms. And that is what we see in this relationship. So in parallel circuits, we can predict which branch will receive the highest current or which branch will receive the lowest current. Do we understand the logic? Do you understand how it is? Right? And to remember this more easily, you can take the example from the real life, and that is about the traffic. So when you go from point A to B, you definitely take out the route, no matter the distance, that has less traffic on it. So traffic represents resistance and current represents the flow of cars or the movement of cars through that road. So majority traffic will divert towards, or higher current will divert towards that route which offers less resistance, less traffic. Similarly, vice versa for the other branch. Okay, this is just one way to remember this. Okay, so now we're going to verify.
You also just
Now we're going to verify, or we're going to understand why the voltage remains same. Again, you are supposed to remember these rules for series and parallel. They are opposite to each other, right? They will help you to identify or simply solve the circuit much quickly instead of just figuring out the rules for them. Okay, so why does the voltage remain the same? The voltage is the energy of electron, right? So let's look at a parallel circuit, simple parallel circuit. There are two ways in which the parallel circuit may be given to you from the examiner side, and I'm going to draw both configurations. They are basically the same thing at the same time. So these are two resistors connected in parallel. How do I know that they are in parallel? Because if I analyze the direction of current coming from the battery, I realize that from this junction the current has two choices. Either the current can flow forward or the current can flow to this branch, right? So I will consider between point A and between point B that the resistor first one, or the first resistor and second resistor, are parallel to each other. The same diagram or the same idea can be given to you in this configuration, and it will not be wrong. It will still be correct. What he can do is he simply connects a battery with multiple cells, then gives you one resistor, and then connects another resistor in parallel to it, and then completes the circuit. These both diagrams are exactly the same. They represent the same concept, the same idea. So even for this diagram, we can see that when the current actually leaves the battery, at this point it has a choice. It is given with the choice to divide itself between two branches, and then it combines together at this branch and continues forward, right? Okay, so why does the voltage remain the same? You see, voltage is the energy of electron. Again, I remind you that that is the energy or work done by each charge, right? So that is joules per coulomb. So when I look at each electron, I'm going to just pick one electron and see what's going to happen with it. So let's say there are a few electrons moving through the circuit over to this direction. Now, have the electrons encountered any resistance from the point they left the battery to the point that when they reached point A? Have they encountered any resistance from the circuit? No. They are just moving through the wires, so nobody is taking energy away from them. So when they reach this point A, they still have the maximum energy that they brought from the battery. And of course, we are ignoring the fact right now that we did in one of our lessons in which we were learning the difference between EMF and potential difference, that even the connecting wires consume some voltage. We are not thinking about that right now. We're considering an ideal situation. So we understand that the electron still has complete energy or still has full energy. Nobody has demanded energy from it. So let's say that a few electrons start moving in this branch and a few electrons start moving in this branch. Again, they still haven't encountered the resistor that is going to take the energy away from them. Okay, fine. Now, once they cross the resistor, they would have lost some energy, and once they cross the resistor, this one, they would have lost some energy as well. Now, when I connect the voltmeter across them in these locations, I realize that the only energy or the only voltage that I get right now is of the battery. The same voltage of the battery is being delivered to each resistor. Again, we are saying that the voltage remains the same. It remains the same because when it reaches this junction, no one or no resistive component has taken the energy away from it. So it has maximum energy. When it passes through the resistor, it gives away all of its energy to that resistor and then continues to move forward in the rest of the circuit, because EMF or the electrons from the other side of the circuit are still pushing them forward. And then the current is going to gather back around at this junction and go back to the battery, right? So do we understand why the voltage remains the same when it reaches all the junctions? Because while it is actually reaching that junction or trying to reach that point, no resistive component takes away the energy from the electron, so they have maximum energy or maximum voltage before they enter the resistor or before they encounter a resistor. Do we understand this point? So this is just a way to remember these rules. He will not ask you about these rules in the examination. He's going to ask you or demand you to solve the circuit, not write down or remember or memorize the rules for them. Okay? All right. So now let's try to solve a circuit that is parallel in nature. So there will be two techniques to solve a parallel circuit. Which one you choose to solve, it's your choice. There is no compulsion by the examiner. Okay, so let's write down a simple question. That is this one. So I'm deliberately drawing three resistors to make the situation more complicated and so that we can enhance our concept regarding that. Let's say this branch, all three resistors are parallel to each other. because the current has three choices when it leaves the battery to enter any resistor as he chooses fit. Okay, so let's say that the resistance of this branch, that is the first one, is 10 ohms. This one is 20 ohms and this one is 40 ohms. And consequently, I'm increasing the resistance of each branch so that we can see that in calculation whether the values of current will be different or not. Now, I remember that the voltage of a parallel circuit remains same. So if I understand that the battery voltage that I'm providing right now, let's say that the voltage that I'm providing is 80 volts. These 10 ohm resistor, 20 ohm resistor and 40 ohm resistor, all three of them will get the voltage that is 80 voltage, that is the same voltage, because that again brings me back to the point. When the electron is actually going to reach these junctions, it would not have encountered any resistor by that point. So before it enters the resistor at this location, for all three of them, it still has the maximum energy because there is no resistance. Only when it crosses the resistance, it will have to give away its energy. Okay, so all these three resistors have. Now I'm going to solve this question by method 1. Method 1 is a bit long, but it gives us many answers that we can suspect that the examiner will ask us later on. So I generally prefer the first method, that is I'm trying to teach you right now. I will also share the second method as well, that will be the same. Okay, so let's find out individual currents of each branch. And I can do that very conveniently because I know that for each branch I am getting the same voltage, but each branch has a different resistance. So the voltage available to my 10 ohms resistor is 80 volts. The current I don't know and the resistance is 10 ohms. So similarly, I'm going to repeat the process for all the branches. Okay, so do we understand how we have used the formula of Ohm's law for each branch independently? And do we realize that all the branches are receiving the same voltage? So I'm using the same value. And for the series circuit, we used the same value of current for all the resistors. Here, we are using the same value of voltage for all the resistors. Do we see that? Right? Okay, so the current in the first branch is going to be 8 amperes. The current in the second branch is going to be 4 amperes, and the current in the third branch is going to be 2 amperes. Now, let's go back to the second rule that we did for this topic. And the second rule was that the current divides, and the idea is that they are inversely proportional. Resistance and current are inversely proportional. Do we see that happening over here? That this branch received the maximum current, that is 8 amperes, and this branch received the minimum current, that is 2 amperes. So the higher the resistance, the lower is the value of current, and lower the resistance, higher is the value of current. Do we see that happening in real life now after calculation? Right?
Yeah.
Okay, all right. So let's move ahead with this one. Now, I have found the individual current of each branch. The examiner can ask you the current of these branches independently, depends on the type of question, or he can ask you the total current coming from the battery. Now, what I can do simply, I know that if this branch has 8 electrons, this one has, let's say, 4 electrons, and this one has 2 electrons. Of course, I'm taking these as electrons as well. Of course, if we go at the back end, we'll have to count the number of electrons, that is the value of Q. 6.25 into 10 raised to the power 18 electrons in one packet of charge. So I'm ignoring that value because based on convenience, I'm going to count them as electron. It's easy to deal with this number in comparison to that one. So this one has 8 electrons, this one has 4, this one has 2. Can you tell me what must have been the current generated from the battery? How much current does the battery would have given? Yes, can you answer that question? Mind you again. So the battery sent in 14 electrons, or we can say 14 amperes of current in total, and each packet had, let's say, 14 amperes were sent by the battery, and each electron had 80 volts of energy to spare. And then they divided themselves according to the resistances of the branches, and of course cross the boundary with the resistor. So the total current generated by the battery in this case would be 8 plus 4 plus 2. So that would be 14 amperes. And if you remember, for the series circuit, what we did was the counter check was the addition of voltage, because in series circuit the voltage divides, and at the end, if I add the voltage of all the circuit components, I will get the same voltage as the source. Over here, since the current is dividing, if I add all the currents, I will get the same value of current that actually exited the battery. Do we understand that series and parallel are actually vice versa circuits of each other? They're actually mirror images of each other. Do we understand that point? Right?
Yeah.
Okay. All right. So,
So
the,
in
the
yeah.
yeah, yeah. So the question asked by the examiner in MCQ or P2 question is generally to find the current of the battery. And sometimes in the following parts, he may ask you to find the current of only one branch. Let's say he may ask you to find the current of 20 ohms. So what I generally do as a student, right, is that I find the current of each branch and then I add them together to find out the current of the battery. Now, this method, although longer, saves me quite a bit of trouble, because generally what the examiner does is, what I've seen, 90% of the cases, he's going to ask me the total current and the current of each branch, one part or the other part. So what students generally do is that they identify that this is a parallel circuit. This is the second method, right? And there is a flaw in this method, and there's a problem with this method. The second method is that what they're trying to do is they're trying to find out the equivalent resistance of the circuit. Now we know that this is a parallel circuit, so we can use the formula that is 10 ohms, 20 ohms and 40 ohms. I can use the formula 1 over RT equals to 1 over 10 plus 1 over 20 plus 1 over 40. Would you be so kind to find the value of RT for me? Can you find out the final value? Yeah. So right now we have 5.71 ohms as our total resistance. So what I can do is, instead of this complicated circuit, I can very well replace my circuit with just one resistor that has a resistance of 5.71. And if you would write down it as a complete fraction, that is 40 divided by 7 ohms. Why am I taking full fraction? Because we want to find out the value of current. If I take 5.71, I may get my current in decimal places, that we did yesterday as well. So my battery is still 80 volts, that is 80 volts. So let's find out the current being generated by the battery, right? So the current by the battery should be V equals to IR. 80 volts are available to me, current is what I want to find out, and the resistance that I want to find out is 5.71. I would advise you that if you can use the fraction directly, that is 40 divided by 7, take 7 over there as a multiple and then divide by 40, that would give you the answer directly. If you use 5.71, your answer will be in decimal. Now it's your choice, but we just wanted to verify the total current. Okay, so 80 divided by 5.71. I'm getting 14.01, which of course is a bit overestimated. But if I write down this as up to two significant figures, I will see that my answer is 14. You should get answer 14 amperes for both of them. Do we get that? Right?
Yeah.
All right. So again, we go back. Did we find this as the total current previously in the previous example? Did we find that? Right? So, but this the problem with this method is that if I had to ask you to find the current of an individual branch, then you'll have to solve the question again. If you had already solved for each branch separately, then you would already have known all the answers to the question. Okay? Now again, there is no compulsion from my side, neither from the examiner side. Whatever method you're comfortable with, you can use that. You can either use method number 1 or you can use method number 2. That's your choice. Okay?
Okay.
Now, do we need to find the voltages of these resistors? We don't need to do that. Why? Because we know that voltages are constant. They are same for all the resistors. The only thing differentiating, or the only differentiating thing between them, is the difference, or is the value of current that is going to flow through them. So that's why I'm not finding the voltages. I'm only finding the currents. Do you understand this?
Yeah.
All right, good. So this is all about the parallel circuits, and this is how we look at them. Now we're going to look at combinational circuits. Now the term combinational is not a term from your syllabus. I just use that for reference of a circuit that has both type of resistor configurations. Okay, so combinational circuits. I'm going to start with a very simple example, and for all the examples we are supposed to find out the voltages, the currents and the resistances. We are supposed to find everything. So I won't have to state them again and again. So let's say this is a battery. This is not a battery but a cell. Let's say this is my first resistor. This is my second resistor. Right now it looks like a series circuit, but I'm going to add one more resistor in parallel with the second one. So let's say this is 10 ohms, this is 20 ohms, and this is 5 ohms. The battery given to us, or the cell that is given to us, is, let's say, 10 volts, right? So what I'm supposed to find out is the current being produced at this point. I will call this IM, or you can say I main current, or the total current. I'm supposed to find out the voltage of this first resistor as V1. I'm supposed to find out the voltage of 20 ohm resistor. Now, do I need to find the voltage of the 10 ohm resistor? I don't need to do that. Why? Because 20 and 10 are in parallel to each other. So whatever voltage is going to show up for 20, it will be the same for 10. The only difference between them will be the amount of current flowing through them. So I'll have to find out individual currents as I1 and I2, which is of course IM, or the main current being divided into this branch and into this branch. Do we understand how we're looking at the question? I haven't started solving it yet, but I'm just making a mind map of what I'm supposed to do with the question. Do we understand that?
Yeah.
Okay. So now the first step would be to simplify the circuit so that I can see that as a single resistor. When I see that as a single resistor, I can find out the main current. So if I want to simplify, I see that 20 and 10 ohms are parallel to each other and 5 ohm is in series. So I will apply the formula 1 over RT equals to 1 over 20 plus 1 over 10 for this branch. So please find out the value of RT over here using the fraction symbol again.
Okay.
So I'm getting 6.67 as 20 by 3, or to be more precise, that will be 6.7 ohms up to two significant figures. So
Yeah, 20 over 3.
all right. So now my circuit looks like this one. I have done the first stage of simplification. I've combined the two parallel circuits, two parallel resistors like this way. So this is my 6.7 ohms and this is my 5 ohms. Now be advised that the representative of these two resistors is now 6.7. They have lost their individual identity in favor of simplicity, or in favor of simplification, right? So the next step would again be very simple. Now since both of them are now in series, I can consider them as a single resistor like this one. So let's say that this is still 10 volts of battery, 10 volts of battery. Now I'll simply add them together. So what do I get? I get 11.7 ohms of resistance. So this complicated circuit that had three resistors, 5, 20 and 10, only matters, or is only impactful, or is only good enough for 11.7 ohms of resistor. So if I had to replace everything in the circuit by a single resistor, that could have been 11.7. So I've successfully achieved simplification. Do we understand this point? Now I want to find out my I main, the current generated by the battery, and for that I need the circuit to be simplified to a single resistor and to a single battery. Now I can find out the main current as V equals to IR, that is 11.7. The voltage that I have is 10 volts, so 10 divided by 11.7 equals to IM. So please use the calculator to find them, collect side by side. So 10 divided by 11.7. I'm getting 0.85.
Yeah, 0.85.
Alright, so I'm getting the current of 0.85 amperes. Okay, let's go back. So I identify that the current in the circuit right now is 0.85 amperes. Okay, fine. Now, for the 5 ohm resistor, if I wanted to find the voltage, do I need to change the value of current, or is that in series to the circuit? If I wanted to find the voltage of 5 ohm resistor, so voltage of the 5 ohm resistor, I will use V equals to IR. What should be the value of current that I should be using?
So will it not be 0.85?
Yeah, it will be 0.85. Why? Because that the circuit or the resistor 5 ohms is in series, the current has no alternate path available to it. So it has to pass through the 5 ohm resistor, and as a result, it's going to lose some energy. That energy is its own voltage. That is what we are trying to find out. That if I had sent in an electron that has 10 volts from the battery, how much energy will it lose when it enters this resistor? Right? Do you understand that idea? Okay, so
Yeah.
0.85 current, because it's in series, no other choice to go through. So this becomes 4.25 volts. My answers should be in two significant figures, but since I'm getting a whole number, I'm not rounding it off to 4.3. So I'm getting 4.25 volt of consumption across the 5 ohm resistor. So if I had connected a voltmeter at this point across the 5 ohm resistor, like this one, voltmeter in parallel, it would have shown me a value of 4.25 volts. Do we agree up to this point? Yes, do we agree up to this point?
Yes. Yes.
All right, all right. Now, coming back to this simplified version, that means that my voltage consumption of 5 ohms is 4.25. Now, since this 20 ohms and 10 ohms, their representative is 6.67, 6.7 ohms, can I say that I can find its voltage by simply subtracting 10 with 4.25, because they are in series right now. So the voltage will be divided among them. Right? So whatever happens with the representative, that will be reflected upon them in the full circuit. Do we understand what we are doing right now? Right?
Yeah.
So my other logic would be that the voltage of 20 and 10 ohms should be EMF minus the voltage consumed by 5 ohm resistor. So the EMF available to my electron was 10 volts, and the consumed voltage from it has been 4.25. So I can simply subtract this from this, and I get 5.75. So 5.75 volts are now available to the 6.7 ohm combinational resistor, 5.75 volts, which again represents the individual identity of 20 ohms and 10 ohms resistor. Do we understand this point?
Yes.
Okay, good. And you can verify this. If you add 4.25 with 5.75, it will give you 10 volts again. So I repeat my statement. What has happened is that 10 volts or 10 joules of energy has divided between the first 5 ohm resistor as 4.25, and the rest of the 5.75 has been received by the parallel combination. But since the parallel combination is difficult to solve, we have simplified this over here to represent or to replace them by a single resistor so that it becomes easy to solve. Once we find out the voltage of their representative, we can now go back to the main circuit, hoping that the V2 value will be 5.75 volts. Do we agree up to this point?
And then we use the separate resistance.
Exactly. Now since, very good. Now since they are parallel to each other, I'm going to redraw the circuit. So this is my first 5 ohm resistor, this is my second 20 ohm resistor, and this is my third 10 ohm resistor. Now I know that the voltage available to the parallel branch in this place or at this place is 5.75 volts. Now since they are in parallel to each other, both of them will be getting the same voltage, right? So I will solve for their current individually, separately, very easily. So I'll get 5.75 equals to I into 20, then 5.75 equals to I into 10. Do we understand what we've done? We've used the same voltage for both of them because they are in parallel. We are using the formula V equals to IR for both branches, right? So please find the value. 5.75 divided by 20 would be 0.29 amperes up to 2 significant. I'm rounding it off, and this will be
0.575.
yes, 0.575. So I'm rounding this off as 5.6 amperes. Okay. Now, can we visually confirm that the higher resistance branch received a lesser current and a lesser resistance branch received a higher current? Can we confirm that? Right? And
Yeah.
what was the current that is entering the branch that was supposed to be divided? That current was 0.85 amperes before it entered this branch. Is that so? Right? So now let's try to verify that is that the same current by adding these two currents together. So I want to find out the main current that entered that branch by simply adding 0.29 with 0.56. So please see what answer do you get, 0.9 plus
Yeah,
0.56.
0.85.
Do we get 0.85, right?
Yeah. Yes. Yeah.
So again, whatever rules we have studied about series and parallel, they are being verified with each part of the circuit. So verily, this current is being divided into two branches. And of course, the trend of the division was higher resistance, lower current, lower resistance, higher current, right? And they received the same voltage, and the voltage was found out by their representative, not individually. We can't do that. We can't use this 20 and 10 ohms right now in this complicated circuit to find out their voltages. I'll have to first convert them to their representative so that it becomes a single entity. And then that single entity or their representative can be used to find out their voltage share from the source. And then we'll go back to the main circuit to see that, okay, these both resistors receive 5.75, and then we can individually find the current through both branches. So right now, this 5 ohm resistor, the current entering this 5 ohm resistor is 0.5, the leaving current is 0.85. That is why the 5 ohm resistor is considered to be in series, because the current has no alternate path. And the voltage it consumes is 4.25 voltage. So 10 volt is what we gave it. The electron reached across this resistor, lost 4.25 voltage, and now it only has 5.75. It is going to offer 5.75 voltage or joules per coulomb to both branches, because until it encounters a resistor, there is no one taking the energy away from it. That is the rule for the parallel circuit, that voltage remains the same. The only thing that we have seen divided in parallel circuit is the current, and we have also verified that yes, they must be coming from some main branch, so from some main node, and that is the entering current into this branch. So do we verify, can we verify all the rules of series and parallel circuit in this combinational circuit? Can we verify them? Right?
Yeah.
So any problems in understanding a combinational circuit?